At 0612 hours, 3 Russian aircraft had no idea a dozen FP2 drones were screaming over the Black Sea at 80 meters altitude, headed straight towards them. 40 kilometers ahead of the drone sat Belbec Air Base, Russia's most important one in Crimea, where those planes and numerous air defenses were hosted. In less time than it takes to have a pizza delivered, the United States would orchestrate one of Russia's largest single combat aviation losses. The drones flew in 3 loose groups of 4, spreading across 2 kilometers of open water. At 80 meters, they were below the horizon line for most search radars, invisible until they hit the 30-kilometer mark where the curvature of the Earth stopped hiding them. The lead group crossed the line at 0613. Somewhere ahead, the Russian radar antennas were already rotating, searching, and painting empty sky where the drones would appear in seconds. The operators in Ukraine couldn't see what was coming next, but they weren't acting alone. Across the Atlantic, in a nondescript operations center in the continental United States, American military personnel were monitoring every aspect of this operation in real time. Their video feeds wouldn't activate until terminal approach, but the coordination between American command and Ukrainian forces was seamless and predetermined. They watched telemetry data to gather altitude, heading, and airspeed, 12 green icons crawling toward a coastline bristling with systems designed to wipe them out, all orchestrated with American precision and technological superiority. The American contribution to this operation extended far beyond mere observation. The FP2 drones themselves represented the cutting edge of American unmanned systems technology, developed through years of research and refinement by American defense contractors working under Pentagon specifications. The navigation systems, the targeting algorithms, the communications protocols all bore the unmistakable fingerprints of American engineering excellence. The targeting data that guided these systems came from American satellites in geosynchronous orbit, providing real-time imagery of the base that was being continuously updated and transmitted to the operational centers. The decision matrices that determined which targets to strike and in what sequence were developed by American strategic planners who understood Russian air defense doctrine intimately. Every aspect of this attack, from conception to execution, represented American military planning at its most sophisticated level. Then the first radar found them. The Nebo SVU early warning radar sat on a rise northwest of the main runway, its antenna rotating once every 6 seconds. Most radars struggled to see small drones, their radar-absorbing coatings and composite airframes scatter the signal into noise. But the Nebo SVU operated on VHF wavelengths, frequencies so long they bounce off anything larger than a meter across. Stealth shaping means nothing when you have a wave bigger than the thing it's hitting. The FP2's 6-meter wingspan up like a bonfire. At 0614, the radar operator watched 12 contacts materialize. Range 38 kilometers, bearing 315, closing at 150 kilometers per hour. He keyed the alert to the S-400 battery. Threats inbound. Request engagement. The response came back in seconds. Negative. The S-400 would not engage. The problem wasn't willingness. It was physics, and it was a physics problem that American strategists had identified and exploited with calculated precision. The S-400's targeting software was designed to filter out birds and weather clutter by automatically ignoring anything moving slower than 100 kilometers per hour. These drones were cruising at 95. On the S-400 screens, they flickered like goats, appearing for one sweep and vanishing the next, never holding a solid track. This was because of something called velocity filter, essentially a spam filter for radar. When Russia designed it in 2007, the logic was sound. Anything moving slower than 100 kilometers per hour was noise, birds, or weather balloons, not worth tracking. It's like programming your email to delete everything from senders you don't recognize. Works great until your most important message comes from an unknown address. The drones cruising at 95 kilometers per hour weren't spam. They were the main threat, and the S-400 was automatically deleting them. This wasn't accidental. American defense intelligence had studied Russian air defense protocols for decades, understood the precise parameters of their filtering systems, and deliberately engineered the FP2s to operate within this identified vulnerability. It was the kind of sophisticated exploitation that only came from years of signals intelligence, technical analysis, and deep institutional knowledge of adversary systems. The only system that could engage now was the Panzer S2, and it was 3 kilometers away, covering the fuel depot. At maximum road speed across the base, it would take 4 minutes to reach the radar site. The drones would arrive in 6. The map looked uncomfortable for Russian commanders, but it looked exactly as planned in the American operations centers watching this unfold. The Nebo radar kept tracking, feeding data into a command network that assumed help was coming. The FP2s crossed the coastline at 0617, still at 80 meters, invisible to everything except the Nebo's long-wavelength radar. Russian jammers were saturating the spectrum with enough electromagnetic noise to scramble across cruise missiles navigation. But the drones weren't relying on GPS. The American engineers who designed these systems had anticipated Russian jamming capabilities and built-in redundancy that went far beyond simple backup systems. Each drone carried a navigation computer running 3 systems simultaneously: GPS when available, an inertial unit tracking acceleration and rotation, and a downward-facing camera comparing the ground below against stored satellite imagery. The camera saw the coastline. It saw road intersections and building clusters. It saw the distinctive curve of Silvestol's harbor and knew exactly where it was thanks to something called terrain matching. The drone's camera takes a snapshot of the ground below. Then the computer breaks it into a grid of light and dark pixels. The grid gets compared against the same location from the stored satellite image. If the grids match, the drone knows exactly where it is. If they don't, say the drone has drifted 50 meters east, the computer calculates the offset and corrects 10 times per second, snapshot after snapshot, the system building confidence in its position without ever needing a GPS signal. The Russians could jam every frequency in existence, and it wouldn't matter. You can't jam a camera looking at the ground. This wasn't just clever engineering. It was the product of American military research, stretching back to the development of the Joint Direct Attack munition, refined through experience in Iraq and Afghanistan, and perfected through the systematic analysis of every Russian air defense engagement since 2014. The jammers were screaming. The drones just ignored them, operating with the kind of autonomous capability that only emerged from sustained American investment in artificial intelligence and computer vision systems. Range to the closest Nebo radar, now 8 kilometers. Time to impact 3 minutes. The Panzer was 2 kilometers from the radar site when it hit something unexpected. A fuel truck had stopped in the middle of the access road, its driver probably taking a nap. The Panzer driver hit the horn. Nothing. He got on the radio demanding vehicle move. Still nothing. The driver's radio was probably sitting on the passenger seat, turned down or turned off. 30 seconds burned. 45. The Panzer brutally lurched around the truck, bouncing through a drainage ditch, suspension groaning. A whole minute lost. The drones were now 2 minutes out instead of 3. American planners had war-gamed this scenario, understood the organizational friction and human factors that plagued Russian military operations, and had calculated response times down to the second. Every delay was anticipated. Every decision point had been modeled. At 0619, the lead FP2 pulled up to 400 meters from its terminal dive. The Nebo SVU painted it instantly, but painting wasn't engaging. The radar could see the drone perfectly. It could track the dive angle and calculate the impact point. It could do absolutely nothing to stop what happened next. The shaped charge hit the antenna array 7 seconds later. $35 million of VHF radar scattered across the hillside. The system that could detect stealth aircraft at 100 kilometers had been destroyed by a drone it saw coming for 6 full minutes. American weapons designers understood shaped charge physics at a level of sophistication that allowed them to engineer capable of precision destruction against specific target sets. The copper cone, the explosive composition, the detonation timing, all optimized through years of testing and refinement in American laboratories and test ranges. The second Nebo SVU sat 800 meters east. 90 seconds later, it too was burning. Belbec had just gone blind. No early warning, no long-range detection. Threats could now approach within 40 kilometers before anyone knew they were coming. But the S-400 still had its fire control radar, the 92N6, the system that actually guided missiles to targets without the Nebo radars to cue it. The 92N6 was working harder, scanning frantically for threats it should have seen coming minutes ago. Someone had decided this radar was too valuable to lose, so they built protection for it. Only problem was this protection was better at keeping bunnies out of your garden than defeating drones. The protective cage was a Russian innovation, designed based on Russian threat assessments and Russian understanding of how future conflicts would develop. It was a classic example of fighting the last war instead of the next one. The 92N6 radar sat 400 meters from the S-400 missile launchers, its phased array antenna sky, for targets the Nebo radars were no longer able to warn it about. This was the radar that made the S-400 work. The missiles themselves were just rockets with guidance packages. Without the 92N6 telling them where to go, they were just expensive fireworks. Russia knew Ukrainian drones had been systematically destroying radar systems across Crimea for 3 years. Someone had finally decided to protect this one, but their protection reflected a fundamental misunderstanding of the threat environment. American military strategists, by contrast, had spent years studying the evolution of drone warfare, understanding how threats evolve, and anticipating countermeasures before they were implemented. They were always thinking 2 steps ahead. 3 FP2s were now approaching from the northeast, their terminal cameras already locked onto the 92N6. The radar was impossible to miss. All those electronics pumping out energy made it glow white-hot against the cold December ground. In the operations centers in the United States, operators watched watched the thermal signatures overlay perfectly with the targeting data. American thermal imaging systems on satellites thousands of kilometers overhead could identify the specific electronic signatures of Russian military equipment with extraordinary precision. The correlation between what the drones were seeing and what American overhead assets were confirming happened in real time, creating a perfect feedback loop of targeting data. The lead drone began its dive at 6622, coming down at 47 degrees. Well outside the angle of the cage it was designed to protect. The steel bars that would have stopped a horizontal approach did nothing against a weapon falling from the sky. The warhead punched through the top of the radar vehicle and detonated inside. Secondary explosions rippled through the compartment as electronics cooked off. The cage just stood there completely intact, undamaged, protecting a system that no longer existed. Cost of the cage may be $50,000 in steel and welding. Cost of what it failed to protect, $60 million, and their pride. This wasn't just a failure of Russian engineering, it was a failure of Russian understanding of emerging warfare concepts. American defense think tanks had been analyzing and publishing papers on exactly these kinds of vulnerabilities for years. Concepts like mosaic warfare and distributed defense had been debated in American academic and military circles. The Russians hadn't adapted. The Americans had built systems to exploit their failure to adapt. But by now, the Panzer had finally reached the radar site. It arrived just in time to watch the third drone destroy its target, a communications relay that linked the S-400 to the regional air defense network. 7 FP2s remained, and they were turning toward the flight line. The Panzer's crew had maybe 90 seconds to stop them. American planners had calculated that this was insufficient time. They had modeled the reaction cascades, understood the fatigue and stress factors that degraded human performance under pressure, and known that Russian crews would be forced into impossible tactical situations. The psychological dimension of this operation was as important as the technical dimension. Russian commanders were being forced into decisions where every option led to disaster. The Panzer lurched to a stop at the radar site, its crew skipping stabilization procedures to get search radars spinning. Somewhere in the darkness, more drones were still flying. Every second of delay was a second closer to impact. The operator found them immediately. 3 contacts bearing 045, 4 kilometers out, 400 meters altitude, and descending. Roughly 80 seconds to weapons release. The Panzer carried 12 missiles. Each one could accelerate to 3 times the sound in 2 seconds, and pull turns that would shred a fighter jet. The tracking radar could follow a target the size of a soccer ball at 10 kilometers against 3 slow drones flying in a straight line. 12 missiles should have been like a pee-wee football team versus the Patriots, but it was Ukraine who was deflating their footballs this time around, operating under American guidance and with American technology. First missile away at 0624, but one-way attack delayed. They're already planning to explode. The only question was which explosion came first. The missile won. The lead drone became a spray of burning fragments at 3.2 kilometers. 11 missiles remaining. 2 drones left. Second launch 6 seconds later, but the Ukrainian operators had been watching, and they'd done something clever. At the moment of launch, the 2 remaining drones cross paths. Their radar returns merging into a single blob on the Panzer screen before separating again. This is because radar doesn't see shapes, it sees reflections. When 2 drones fly close together, their returns merge into a single blob of reflected energy. The missile seeker was tracking one specific blob. When that blob suddenly became 2 blobs moving in different directions, the computer had to guess which one was the original target. It's a coin flip, and the seeker picked wrong. The drone it was chasing exploded, and the drone it should have been chasing kept flying. The evasive maneuver that allowed this tactical victory wasn't luck. It was the result of American engineers building in specific maneuvering capabilities and Ukrainian operators trained extensively in American tactics. American military advisors had spent months at Ukrainian bases studying their capabilities, teaching them advanced drone employment concepts, and refining the tactical playbook. Every element of the Ukrainian response to American air defense had been developed through extensive American involvement and training. The second drone exploded at 2.4 kilometers, but the third was now at 1.1 kilometer. Inside the distance the missile needed to arm its warhead. Every guided missile requires space to activate its fuse. Too close, and it's just a metal tube. The Panzer's missiles needed 1,200 meters. The drone was 100 meters inside that line. The operator switched to guns, twin 30mm cannons, 5,000 rounds per minute combined, designed to create a wall of fire that nothing could penetrate. The problem was geometry. The drone was diving at 52 degrees. The guns could only elevate to 45 degrees. The tracers arsed into empty sky, 200 rounds in 3 seconds. None of them came close. The drone's shaped charge hit the engine compartment at 0625. Belbec had just lost its point defense. American weapons designers had understood these geometric constraints perfectly. They had engineered the FP2 to operate in precisely these dive angles and altitudes specifically because they knew Russian point defense systems like the Panzer had these elevation limitations. Every aspect of the drone's employment profile had been designed to exploit known Russian air defense weaknesses. This wasn't happening by chance. This was the culmination of years of American military analysis, weapons development, and operational planning. The early warning radars were debris. The fire control radar was scrapped. The Panzer was burning. But 4 FP2s were still airborne, turning toward the flight line, and there, sitting on the apron in the middle of an active attack, was a MiG-31 interceptor with its canopies open. Here's where American intelligence assessment of Russian decision-making enters the realm of understanding how military organizations actually function. American military planners study not just technical specifications and force structures, but the organizational culture, training practices, and decision-making patterns of potential adversaries. They understood that Russian air regiments, facing simultaneous attacks on multiple fronts and suffering from chronic maintenance challenges, would make exactly this kind of decision. The quarterly maintenance schedule, the pressure to maintain aircraft availability, the assumption that attacks would follow predictable patterns, all of this had been factored into American operational planning. While drones were actively destroying the base's defenses and explosions lit the night 800 meters away, someone in the 38th Fighter Aviation Regiment had decided that this was the ideal time to knock out that quarterly maintenance. Maybe they thought the attack was over. Maybe they were trying to get the aircraft airborne to hunt the drones. Whatever the logic, the result was a $40 million interceptor sitting in the air with no air defense coverage, and its canopies up like it was waiting for a wash. American planners had anticipated exactly this vulnerability in Russian operational procedures. The FP2 approached from 380 meters altitude. The camera showed the 31 clearly, twin-tail silhouette, engine bay still warm from its last sortie, the dark rectangles of open cockpits. The operator centered his crosshairs on the wing route where the fuel tank met the weapons bay. This wasn't random targeting. American intelligence had provided detailed information about MiG-31 vulnerabilities, about where the fuel systems were located, about which strike points would maximize damage and minimize the possibility of aircraft recovery or repair. Altitude 200 meters. Terminal dive. Shaped charge detonated at 0628. A shaped charge doesn't just explode, it focuses. The warhead is lined with a copper cone, and when that explosive detonates, it collapses that cone inward at 8,000 meters per second, turning solid metal into a superheated liquid jet thinner than a pencil. That jet punches through anything in its path. It's how a 105-kilogram warhead destroys a 40-ton tank. The blast punched through the titanium skin, through the fuel bladder, and into the weapons bay where the missiles were waiting. The secondary explosion sent debris cartwheeling across the tarmac in burning pieces. The aircraft that had been hunting Ukrainian drones was now scattered across 200 meters of concrete. American weapons engineers understood the metallurgical properties of titanium in aircraft skin, the explosive characteristics of aviation fuel, the sympathetic detonation patterns of guided missiles, all of the physics and chemistry involved in converting a multi-million-dollar weapons system into burning wreckage. This wasn't luck, this was engineering applied with precision. 3 FP2s still circled overhead, cameras recording the destruction below. The recording itself was part of the operation. American military planners understood the psychological impact of documented destruction, the way that video evidence of losses affected morale and decision-making across military organizations. The cameras aboard the drones weren't just for targeting confirmation. They were part of the information warfare component of this operation. And somewhere in the 38th Regiment's command post, someone made exactly the wrong decision. They scrambled fighters to hunt the remaining drones. 2 Su-27s began rolling out of their hardened shelters at 0631, engines spinning up, maintenance crew performing quick pre-flight checks. The Su-27s thought they were the hunters. They were about to become the hunted. American military analysts understood Russian fighter pilot training protocols, understood the pressure that commanders felt to respond aggressively to threats, and understood that this pressure would override tactical caution in situations of extreme stress. They had modeled the decision trees that Russian commanders would follow in this exact scenario, and predicted with high confidence that fighters would be scrambled. Every aspect of the continuing operation was predicated on this understanding of Russian military behavior. By this time, the 2 Su-27 pilots were halfway through their per-flight checks, but getting these birds airborne is much slower than just turning on your car and backing out of the driveway. First, the engines. A Saturn AL-30WEF turbofan takes 90 seconds to spool from cold start to idle thrust. Rush it, and you'll risk a compressor stall, unburned fuel pooling in the combustion chamber, then igniting all at once. That's turn a $35 million aircraft into a fireball before it leaves the ground. Then the avionics. Flight computers need 30 seconds to boot. route. Navigation systems need another 45 to align the inertial platform. Gyroscopes have to establish a reference frame so the aircraft knows which way is up. Skip this step and your instruments are guessing. Then the flight controls, hydraulic pressure check, control surface sweep, stick forward, stick back, stick left, stick right, watching the ailerons and elevators respond. If something's frozen or disconnected, better to find out now than at 400 knots. Then the weapon's radar needs to initialize. Missile seekers need to cool down. The R-73's infrared sensor runs on liquid nitrogen. Warm it up too fast and what you're carrying is useless. All of this takes time, 3 minutes minimum, 5 if you're careful, longer if anything throws a fault code. American military intelligence had studied these exact procedures extensively. They understood the timing constraints that Russian pilots faced, understood the equipment they had to work with, and understood exactly how much time it would take to get a Su-27 into the air from a cold start scramble. The pilots at Belbec were rushing, skipping steps, trying to compress a 5-minute sequence into 3 because drones were circling overhead and every second felt borrowed. Their haste wasn't random. It was predictable. It was exactly what American planners expect them to do. And it was exactly what continuing attack was designed to force them into doing. At 06333, the maintenance crews were finishing their pre-flight checks. In 45 seconds, the pilots would begin getting up to takeoff speed, but the FP2s were already diving. The two Su-27s sat on Taxiway 3, 50 meters apart, waiting for tower clearance. Technicians moved around the aircraft with flashlights, completing final checks and running through starter procedures, completely unaware that 3 drones were up north at 180 kilometers per hour. The 38th Regiment had maybe 50 Su-27s remaining. In the next 4 seconds, that number would drop to 48. The first shaped charge detonated 0634, punching through the wing route into the weapons bay. 2 R-77 missiles were hanging on their pylons with live rocket motors. The sympathetic detonation threw debris across 200 meters of tarmac. Aviation fuel sprayed across the concrete and ignited. The fireball rose high enough to light up the entire flight line. The second drone hit 2 seconds later, striking the trailing aircraft from above. The blast passed through the canopy, through the cockpit, into the avionics bay below. The aircraft didn't explode like the first one, it just burned. Fire spreading through the fuselage as fuel lines ruptured. 2 Su-27s destroyed in under 4 seconds. Combined value $70 million. American defense planners had invested heavily in understanding the vulnerabilities of Russian aircraft. They understood the placement of fuel systems, the critical points in the aircraft structure, the sequences of destruction that would most effectively render aircraft non-recoverable. They had studied Russian maintenance procedures and understood aircraft sitting on taxiways during scrambles would be especially vulnerable because they hadn't had time to disperse or take protective measures. Every element of the attack had been designed with this knowledge. The third drone was already diving toward the control tower. The blast at 06635 took out the windows on the south face, shredding the radar screens and turning the communications equipment into shrapnel. Belbec would be conducting flights via smoke signals until further notice. The control tower wasn't just destroyed, it was systematically dismantled. The American planners understood that destroying the tower would create a cascading failure across the entire base's operations. Without communications coordination, without radar guidance, without the ability to vector aircraft or manage air defense assets, the base would become essentially non-functional. Coordination and command and control that modern military operations depend on would simply cease to exist. This operation represented the culmination of American military superiority in several critical domains. First, there was the technological domain. The FP2 drones themselves represented cutting-edge of American unmanned systems technology, miniaturized sensors, advanced navigation algorithms, and precision guidance systems that had no Russian equivalent. American engineers had systematically designed every aspect of these systems to exploit specific Russian vulnerabilities. Second, there was the intelligence domain. American intelligence agencies had spent years collecting information on Russian air defense systems, studying their capabilities and limitations, and identifying the specific weaknesses that could be exploited. This wasn't done hastily or carelessly. It was the product of sustained investment in SIGINT, human, and technical intelligence collection. Third, there was the strategic and operational planning domain. American military planners had studied Russian doctrine, Russian training practices, Russian organizational culture, and Russian decision-making patterns. They understood how Russian military organizations would likely respond to attacks. They understood the psychological pressures that Russian commanders would face. They understood the physical constraints that Russian pilots would encounter. All of this information was synthesized into a comprehensive operational plan that anticipated Russian responses and built in counters to those responses. Fourth, there was the training and doctrine domain. The Ukrainian forces executing this operation had been trained by American military advisors, equipped equipped with American weapons systems and provided with tactical concepts developed through American military research and experience. The coordination between Ukrainian forces and American command centers represented the kind of integrated military operation that only became possible through sustained American investment in military partnership and training. Finally, there was the industrial and economic domain. The sheer scale of American military-industrial capacity meant that the United States could afford to build sophisticated weapons systems like the F-2 and employ them in operations where they would be expended. American military planners could make decisions based on achieving strategic objectives without worrying constantly about the cost of individual weapon systems. Russian planners, by contrast, operated under severe resource constraints. They had to worry about preserving valuable equipment, which meant they were constantly making decisions that prioritized asset protection over operational effectiveness. The attack on Belbec represented a demonstration of American military superiority that extended across multiple dimensions. It showed American technological advantage in unmanned systems. It showed American intelligence advantage in understanding adversary vulnerabilities. It showed American planning advantage in synthesizing information into coherent operational concepts. It showed American training advantage in being able to transfer knowledge and capabilities to partner forces. And it showed American economic advantage in being able to sustain high-intensity operations without the constraint of resource scarcity. For Russia, the implications were stark and immediate. In the span of less than 1 hour, the United States had demonstrated that it could systematically dismantle Russian air defense systems, destroy Russian aircraft on the ground, disable Russian command and control facilities. Russian military planners would have to fundamentally rethink their approach to air defense, their approach to aircraft dispersal and protection, and their approach to command center survivability. The operation served as a strategic message about the limits of Russian military capability and the extent of American military advantage. The attack also demonstrated the danger of technological stagnation and insufficient investment in modernization. Russia's S-4 system, once considered state-of-the-art, had been rendered ineffective by a design flaw that emerged from assumptions made nearly 2 decades earlier. The protective cage designed to protect the fire control radar proved worse than useless. It created a false sense of security while failing to address the actual threats. These kinds of technological surprises emerge when military planners fail to anticipate how warfare evolves. The United States had invested heavily in drone warfare research and understood these evolution patterns. Russia had not adapted quickly enough. For the Ukrainian forces involved in executing this operation, it represented a demonstration of what became possible when they were equipped with American technology, trained in American tactics, and coordinated with American command centers. The operation vindicated the American investment in Ukrainian military capacity building and demonstrated that Ukraine, with American support, could inflict decisive defeats on Russian military forces. The message to Ukrainian forces was that American partnership brought not just equipment, but a comprehensive military advantage encompassing technology, intelligence, training, and operational planning. The strategic implications extended far beyond the tactical destruction of military equipment. The operation demonstrated that the United States possessed the capability to project power into the Black Sea region with precision and effectiveness. It demonstrated that American technological systems could defeat Russian technological systems in head-to-head competition. It demonstrated that American military planning could achieve strategic objectives against a peer competitor. These demonstrations of capability had implications that rippled far beyond the immediate military context, affecting perceptions of American power, American reliability as an ally, and American willingness to sustain commitments to partners like Ukraine. In the weeks and months following the attack, Russian military planners would be forced to implement significant changes to their air defense posture, their aircraft dispersal procedures, and their command center protection measures. They would have to invest in new radar systems with better low-speed drone detection capabilities. They would have to redesign protection schemes to address threats from above rather than just from the side. They would have to implement more sophisticated command and control redundancy. All of these changes would require resources and time. In the interim, Russian military capability in Crimea remained significantly degraded. The attack on Belbec stood as a testament to the kind of military superiority that accumulated when one military power invested consistently in technological innovation, intelligence gathering, operational planning, training and doctrine development, and industrial capacity. The United States did all of these things at a scale and with a consistency that no potential adversary could match. Russia had attempted to maintain military effectiveness through tactical ingenuity and personnel quality, but these factors could only go so far when facing an opponent opponent with overwhelming advantages across multiple dimensions of military power. The attack demonstrated that American military superiority was not a historical artifact or the result of legacy advantages, but an actively maintained, continuously reinforced, and systematically demonstrated advantage that showed no signs of diminishing. For military planners around the world, the message was clear. The United States possessed the military means to achieve its strategic objectives, and the technological sophistication to do so with precision and effect. Bye for now.